So we'll be doing the case B, where you will be dealing with complex roots. This is, if you're familiar with how to deal with complex numbers, this is probably the less exciting solution type you will find. But if you haven't had much experience with this, this could be also the most complicated one, or the one that has more source for making mistakes. So as I did in the other case, I would like to start this also with a solution of a specific one. Again, this is from Grimaldi. So the recurrence relation, an equals 2an minus 1 minus 2an minus 2, defined for n bigger or equal to 2, with these initial values. Again, this format, this type, everything is exactly the same, just the characteristic equation will have complex roots, right? So we start with this. And then we get sorry, this is n minus 1. If you factorize n minus 2 and a, you get r squared minus 2r plus 2 equals 0. So the characteristic equation is r squared is 2r plus 2 is equal to 0. So if you look at the roots, you get plus b squared minus 4ac divided by 2. This part is 4 minus 4, so it's 2 plus minus square root of minus 4. You can see that this is 1 plus minus square root of minus 1. Now, in complex number theory, you use I for complex numbers, so you get this thing, which is two complex numbers, right? Two complex numbers, two complex roots. And that's why the case is called complex roots case. Now the general solution is A1, 1 plus I n plus A2, 1 minus I n. But since it is complicated to find powers of complex numbers, we also note that this is a recurrence that you start with numbers like 1, 2, and then you apply this linear equation to get other numbers. So all the numbers you should be getting are integers, like real numbers. So finding something like this is not elegant. I mean, this involves 100 power of complex number, for example. This is not very nice because at the end you want to get some integer, and this looks very ugly for what you want to get. Okay. We want to find a more suitable general form, more suitable general form using angles. So it's like easier to calculate some way that you can calculate with your hand calculator. These things, I mean, unless your hand calculator is very complicated, like very sophisticated, you can't calculate n power of 1 plus I. Like you can't calculate 75th power of 1 plus I in a hand calculator. But we want to find some formula where you can calculate with hand calculator. That means something that involves cosines and sines and so easier to calculate. So to do this, what you need to do is to understand what the complex numbers are about. So first of all, with the complex numbers, what we do, the typical complex number looks like this, right? A plus bi. We denote them on xy plane using one coordinate A here and B coordinate is here. So now you can express your complex numbers in Euclidean two-dimensional plane by using its A part and B part, the I part. Okay. Now, but once you put it there as a point, you see that there will be an angle here, and there will be a distance to 0. The distance to 0 is easy to calculate and usually called augmentation, like the norm of this complex number. And this, the distance between z and 0 is just the sum of the squares of these two distances because it's a right angle and in square root. So it's equal to a squared plus b squared in square root. So we know that that z is equal to that. But also on this line, if you length is z, there is a point which has exactly distance 1 to 0. Those points are called unit circles. So the distance 1, all the points which has distance 1 to 0 are actually nice part of the complex plane. You can see that for those ones, because you know the angle, you can actually find its coordinates very easily by using trigonometry. See, for those ones, the coordinates will be this distance and this distance, right? But you already know that when this is theta and this is 1, this distance should be sine theta. That's basic trigonometry to you, because this divided by this should be sine. And we know this is 1, so it has to be sine theta. Same way, this distance should be cosine theta. So every point on the unit circle has coordinates cosine and sine. Okay? So these points here are cosine theta plus I sine theta. We know that. We actually denote them by e to the I theta to make it more even. But this tells me that if the distant one has these coordinates, when the distance is z, it should be z times the same coordinates, because it's linearly moved towards the z by multiplying with the length, by the basically ratio of the triangles. So this tells me you can express a complex number using its distance to 0 and the angle. And this is one of those nice things about complex number theory. So you can put this e theta, just it's a notation. Okay, so if you want to calculate n power of an integer, like here we did, you'll be taking the n power of this. So that means you'll be taking n power of this real number, and then n power of this this thing. It turns out this is directly proved by the move, I guess. This is called the move. If I'm right, I don't want to write the wrong name. The move. The move. I don't know how to say it. So this is a V. He showed that if you want to take the n power of, you get cosine n theta plus I sine n theta. It's as simple as that, that n goes inside. To remember this formula, you can take this as, if you took the n power of this, you'll be only getting this, so the angle will be just n theta. Okay. There are a couple of different ways to see it. But, this follows from the angle summation formulas. Okay. But if you have such a thing, then look at what we had here, 1 plus I. Remember we had 1 plus I here. So for 1 plus I can do the same, I can discuss this for 1 plus I. So for 1 plus I, I'll have distance 1 and distance 1's here. So its distance to 0 will be square root of 2. And the angle will be 45 degrees. And in radians, it is pi over 4. So 1 plus I is square root of 2 times cosine pi over 4 plus I sine pi over 4. So you can easily write it by calculating its distance to 0 and then finding the angle. So each time you see a complex number, you'll have to do this. Once you find this, then life is easy because with 1 minus, you get minus sign here. So then this general form this thing becomes this. So you get square root of 2 to the power n cosine n pi over 4 plus I sine n pi over 4 plus same thing with the square root of 2 n plus a2 square root of 2 n cosine n pi over 4 plus minus I sine n pi over 4. Now, our focus earlier was these two numbers, and we wrote everything as a combination of them. But when we change it to this angular form, now our focus is these numbers. We treat them as if they're solutions, and then we try to write things using them. So there's square root of 2n will stay there, and then you have coefficients. Those coefficients you can specifically calculate using this, like it will be a1 plus a2 or ia1 minus ia2. But what we do, this is the crucial part, instead of calculating those and putting them here, we declare new coefficients, b1 and b2. And we say this is the general form, general solution for complex case. You may say, there were so many things there, we lost all of it. No, we didn't lose anything, because A1, A2 we didn't know anyway. We just had some unknowns, but I just changed my unknowns to B1 and B2. You can specifically say B1 is what is in terms of A1, A2, but doesn't really matter. Okay? It doesn't matter, really. You forget about A1s and you just take this as your general solution. The advantage of this one is that this sign is a real number, cosine is a real number. B1 and B2 is something you calculate using initial values. So they will turn out to be real numbers too. So actually in this form, B1 and B2 are real numbers. Here actually A1 and A2 are complex numbers. You can see that when these are real numbers, the only way these real numbers are these are complex numbers. So you really didn't want to work with A1, A2 anyway. They were complex numbers. Now you got rid of it and you have real numbers. So all you should care about at this point is if I have a complex roots, I will write it in the angular form. And using that angular form, I will write the general solution by imitating each piece. Just this is how, from here to here, you need to be able to pass each time. Each time you see the roots, you write it like that in angular form, and then you say, this is my general form. Okay. So, for this question, what we need to do to finish it, for this one, is to use initial values to calculate B1 and B2. Okay. So, to finish, we need to use A0, A1, 2 to calculate B1 and B2. Once you calculate B1 and B2, you have a specific solution. Before you have a general solution. So A0 equals 1 on the left side because of the given initial value. On the right side, this is square root of 2 to the power 0, so you just get nothing. And then cosine, like B1 of cosine 0, B2 of sine 0. Okay? So most of the time you actually get very, very clear things. Sine 0 is 0, cosine 0 is 1. This is equal to 1. So you get B1 actually in this. So it's very nice. With A1 being 2, you get this. This time you get cosine pi over 4 plus B2 sine pi over 4. Which again, you need to know what cosine pi over 4, sine pi over 4 is. But it's often very concrete calculation. So from this, you get 1 equals to B1. And then 2 equals to square root of 2 times B1 times this thing is square root of 2 over 2. This one is square root of 2 over 2. So you can see that that gives you B1 plus B2 is 1. So B1 plus B2 is 2. So from this 2, you get B2 is equal to 1. Okay? So you solve this system by basically the same way you solve all the other systems. And now you conclude that solution, this is specific solution, is then an is equal to square root of 2 to the power n cosine n pi over 4 plus sine n pi over 4. So this is this answer to the question for n equals bigger equal to 0. So this is how you do the complex. Do you have any questions or? Any remarks? I mean, this thing is the only difficult part here, but you can actually skip from here to here. In each time you're solving questions, you just need to write this and solve for B1, B2. I wanted to explain why you have this situation. Yeah. Okay. That's the relational. I should warn you, I mean, the complex case is hard because there's more calculations involved with angles, and people tend to make mistakes. So instead of square root of 3 over 2, you take square root of 3, you make mistakes. So as long as you are careful, complex case should not bear any more difficulties than the real case. It's just very standard. But because it involves some of the complex numbers like angles, and you make mistakes, and because of that, people usually consider the complex case the hardest case. Okay. Okay, so how much of matrix theory you know? Do you know matrices, like how to calculate determinants? Everyone saw determinants. Everyone knows. Anyone who doesn't know? Okay, there is this question in the book, which I like, which uses determinants. So I would like to solve this one. So for a positive real number, consider the n by n determinant dn given by, so this is the, so you have bb 0, 0, zeros, then you shift by 1, you put 3 b's, and then you start shifting. Okay, but the rest is 0. Okay, so anywhere I didn't put any number is 0. So let me now put them. So anything that I didn't put is 0. And then you continue. And the last one is again BB. That's kind of weird. Calculate the n for all n in terms of p. This is an example that tells you that why you need to know recursion. I mean, this kind of situation may happen. You may need to calculate the determinant, which looks like generic complicated thing. And you immediately see that it is easy to reduce it to smaller cases, but then you need to know what the solution to smaller cases. So eventually you realize all you get is a recursion, and then you need to solve that recursion. I mean, to be able to solve a question, you need to solve the recursion. At some point, I will try to give you more examples of recursion mixed up with some other questions. So, but this is one of them from the matrix theory, that you can have recursion. Again, it's always good to look at some earlier cases, like n equals 1, n equals 2, n equals 3 cases, because there are, you will first need initial values. Also, you will need to understand the problem better. So in this, because of these reasons, it's good to know small cases. You see that D3 is something that you can talk about, because it will start like this, and then it will end with 2 b's. So D3 is something you can talk about. You can also see D4 like this. So these determinants you can calculate using standard determinant theory. D2 you have to decide. I think D2 will be BB and then BB. So it doesn't look like. Because you have to end with two B's and start with two B's, so that's the only way I can think of. And hopefully get a feeling for what should be happening. So this is how phi will look like. Now, something about determinant theory is that there is this what's called adjoint expansion. So you can choose a row and expand your determinant using the terms in the row as this times the minor that you obtain when you erase those columns and rows. So if you use that expansion with respect to the row, you can see that this will be b times determinant of what is left here. And then this will be minus b times, when you erase these things, you get this. Something like this. Everyone knows, like when you erase this row, you get this BB0, BB0, 0, BB. Is that right? Yeah. What you get here, if you erase this row, you get B times the rest. So B times this. Minus B times what you get when you erase this. BB, 0, BB, 0, BBB, 0, 0, BB. Do you see any pattern so far? Now one more trick I will do so that you can maybe see the pattern. Here we did it with respect to that row, but we could do it with a column. So if you use this column, this will be B times this matrix. So actually you get B times this remaining one. So maybe this will tell you what's going on. So can you tell me what D5 is in terms of D4 and D3? So it's B times D4 minus B squared times D3. And this is true for any n. Like I could have write it using this. It will be harder to write, but you can expand it with respect to this b, now with respect to this b, and then you expand with respect to b, you get d squared. It's actually true here too, that this is equal to b times d3 minus b squared times d2. So it's d4 is also written in terms of the purest. The story here is that because d2 is 0, some of these things like this is going to be 0. But really it still holds the recursion that we want to hold. So, for example, this is going to be b times d2, and then we don't have d1, so it's going to be b squared times b. This is 0. So this is actually minus b cubed. So you can calculate it if you want. So if you put it here, minus b cubed, you get minus b to the 4. And you could try to see if you can get something simple like minus b4, b5, plus you get 0. So probably it's going to be some sort of 0 and b ends, and something like that. Okay. But at this point, we don't know how to conclude what dn is. Just because we see a recursion, so doesn't mean we know the solution. So here what we observe is that there's a recursion. So we observe that there is a recurrence. dn is equal to b dn minus 1 minus b squared dn minus 2. Now the recurrence holds for d4. What you can do, this is a clever trick you can do. You can set d1 is equal to b, just by choice, and then this will be b d2 minus b squared d1. So recurrence will hold for 3 as well. So we can say this is d1 is b, d2 is 0. So you can take these two values, and then you can say recurrence holds these values. Yeah, I could even set d0 to something, but let's not do that. So we can say this is now true for n bigger or equal to 3. Right? So d1 is b, d2 is 0, and for n bigger or equal to 3, dn is equal to that. This stage, this part of the question is the hardest part. As you see, we had to make some choices, set it up right, make sure the recurrence is correct. So setting up the recurrence out of a word problem is the hardest step. And you have to be careful with many things. But we can check quickly if D3 works, and so on. You can see that is all true. Okay, now we can forget about the problem and just try to solve this. The B should not discourage you. B is just some variable. So this is same kind of problem that we have been solving. To solve this recurrence, we use the same strategy, where we just set up dn a times some rn, and then try to solve it for rn. you should see that this is going to give you this characteristic equation. Okay. So the characteristic equation is r squared equals to br minus b squared. From here, you get this r squared minus br plus b squared is 0. This is your quadratic form. B is your variable. B is something that you could ignore as like a number. And now you can try to see what the roots are. You have complex roots. So that's the whole thing, that you get complex roots. So this is b times 1 plus minus square root of 3I over 2. So it's some complex numbers times b. B is, again, you can ignore it. Like b is always going to be carried out. I mean, you can even say that I factorize b out. And so it's going to be reasonable. So you have to just focus on this part. Complex roots, complex part. Okay, so I'm going to give you homework some point. Once I finish this, I think we can do it. So let me forget. Maybe I should write it. Okay, this is homework next week. From Grimaldi. We're doing section 10 there, recursion. 10.2 is all the second orders, 10.1 is first order. This is just a question about banking, a very easy question. I just wanted to put it so that you see the connection to banking. But these recurrence questions are these ones. This one is like A, B, C, D, E, or there's lots of recurrences. Solve all the recurrence questions there. I mean, that if you're going to do something good for final to yourself, treat yourself with this question 1. Solve all the recurrences so that you remember all the real complex other roots. And then solve to any, or 30 if you can. These are the word problems that reduces to recurrence. So you get to know how to reduce recurrence questions to the word problems to recurrence equations. If you do them, you will be very ready for final exam. Okay, let's continue. So I have this. What's that? So there's b, but other than b, this is b times 1 plus square root of 3 over 2. I can forget about the minus part. So the this is z, the normal